Hello student, I am Dr. Ajay Kumar Sinha. Today I am going to discuss wave nature of electromagnetic radiation. Actually, before understanding Bohr's model of atom, three things you have to understand. First, wave nature of electromagnetic radiation. Second, particle nature of electromagnetic radiation. And third, dual behavior of electromagnetic radiation. Only then you can understand Bohr's model of atom. That's why the term developments leading to the Bohr's model of atom is discussed. Then now I am going to discuss wave nature of electromagnetic radiation. Some question is asked on this concept. That's why I am starting only from wave nature of electromagnetic radiation. James Maxwell in 1870 was the first to give a comprehensive explanation about the interaction. Here, what interaction you have to understand. Explanation about the interaction between the charged bodies and the behavior of electrical and magnetic fields on macroscopic level. Macro, big things, not a small. Macro, MAC, macroscopic level. He suggested that when electrically charged particle moves under acceleration, alternating electrical and magnetic fields are produced and transmitted. Not only produces, it transmits also. These fields are transmitted in the forms of waves called electromagnetic waves or electromagnetic radiation. Light is the form of radiation known from early days. We know about the light. Light is the form of radiation known from early days, and speculation about its nature dates back to remote ancient times. In earlier days, means Newton's time, light was supposed to be made of particles. Here, particles are called corpuscles. It actually, this light particle is called corpuscles. It was only in the 19th century when wave nature of light was established. Maxwell was again the first to reveal that light waves are associated with oscillating electrical and magnetic character. Although electromagnetic wave is complex in nature, here I will try to give you idea. It is difficult actually, its nature is difficult, complex in nature. Then here what is actually this electromagnetic wave, that what is its properties, now I will discuss. First properties. First you should understand what is actually this wave nature of electromagnetic radiation. Then what is this electromagnetic radiation? First, I will tell about this wave only. I will give you some idea. It is difficult to understand, but now I am trying to convince you. Actually, suppose some wave passes from, suppose from south to north, south or east to west, you can understand. Suppose some wave is there, just like air flows, air flows. Then from, suppose it is flowing from east to west, just like one line you think, one line, a straight line you consider that it is the air is blowing in that direction from east to west. One line you consider, east to west. Now again three things you have to consider. First, one line you consider that air is blowing from east to west through that line. Only one line you consider. Now second things you think, from the up one wave is coming down through that line. Again it is going up, again it is going down, again it is up, again it is down, again it is up, and again it is meeting that line towards west direction. That is the second concept, second things you have to consider. Third things, now again you think that another wave is starting from down and going up, again coming down, again up, again down, again up, and like that way. Again suppose it is meeting to the same line towards west. Both waves are meeting again only on that line. Then obviously both wave will meet to each other. Somewhere both wave will cross, both wave will meet to each other. Then both waves are perpendicular to each other. Perpendicular to each other. I told you one is coming from up to down and other wave is going from down to up. Then like that way two waves are there and both waves are just perpendicular to each other and they are cutting to each other somewhere, and finally they are meeting on the same line. This is what I have told you, that one wave is the electrical field. One wave is electrical and other wave is magnetic. That's why it is called electromagnetic. Electromagnetic, electric plus magnetic. Both terms are associated. Hence the term electromagnetic. Then light wave. Light flows like that. Light is the example of electromagnetic wave. Then light flows like that. It moves in a vacuum. Actually water wave, for that air wave, water wave, for that medium is required. Some medium is required, either solid, liquid or gas. But for the electromagnetic wave like light, no medium is required. In vacuum it moves. Then now I have given idea. Now I am telling about some few simple properties. Then first property of the electromagnetic radiation is that the oscillating electric and magnetic fields produced by oscillating charged particles are perpendicular to each other and both are perpendicular to the direction of propagation of the wave, what I have told you. Now, second point I am going to discuss. Unlike sound, actually just not like sound, unlike sound waves or water waves, electromagnetic waves do not require medium and can move in vacuum. This is the second property. Third property, it is now well established that there are many types of electromagnetic radiation which differ one another in wavelength or frequency. These constitute what is called electromagnetic spectrum. Different regions of spectrum are identified by different names. Some examples are: first example, radio frequency region, around 10 to the power 6 Hertz. Hertz is the frequency per second used for broadcasting. Second example, microwave region, around 10 to the power 10 Hertz, used for radar. Third example, infrared region, around 10 to the power 13 Hertz, used for heating. Like that way, fourth, ultraviolet region, around 10 to the power 16 Hertz, 10 to the power 16 Hertz, a component of sun's radiation. It is not found, but nowadays some UV rays are coming towards Earth due to depletion of ozone layer. The small portion around 10 to the power 15 Hertz is what is ordinarily we call visible light. Its frequency is 10 to the power 15, and UV I told you 10 to the power 16. Then visual light means daily we see that light. Its frequency is 10 power 15. Then now I have discussed some examples of electromagnetic spectrum. And visual light, I am talking about the visual light now. It is only this part which our eye can see or detect. Our eye works only in visual light. We can't see other light. What I have discussed many reasons that our eye will not work. Our eye works only in visual light, or you can tell we are blind for other lights. Only our eye works in visual light. It is only this part which our eyes can see or detect. Special instruments are required to detect non-visual radiation. That's why we tell non-visual. For other radiation, we use the term non-visual radiation. Next properties, that is the fourth properties. Different kinds of units are used to represent electromagnetic radiation. Different type of units. Examples I will discuss. These radiations are characterized by the properties, namely frequency and wavelength. We discuss in term of we represent radiation in terms of frequency and wavelength. The SI unit for frequency which is represented by nu, a small v like that. The SI unit of frequency nu is hertz, that is a hertz per second, s small s minus 1, hertz per second. After Hendrik Hertz, he was the scientist, only his name, this hertz per second. It is defined as the number of waves that passes a given point in 1 second. Wavelength should have the units of length, and as we know that the SI unit of length is meter, small m, meter. Since magnetic radiation consists of different kinds of waves of much smaller wavelength, smaller units are used. And this electromagnetic radiation which differ from one another in width and frequency, that is actually you can represent in terms of smaller units, because they have very small units. In vacuum, all types of electromagnetic radiation, regardless of wavelength, travels at the speed, that is 3.0 into 10 to the power 8 meter per second. Exactly, if you want, we can tell 2.997925 into 10 to the power 8 meter per second. This is called the speed of light, and in a very simple way we can tell 3 into 10 to the power 8 meter per second. This value always you keep in mind, because it is used in solving the numericals, and it is represented by a small c. The frequency, that is nu, wavelength lambda, just like reverse of y. What you are writing y just in a reverse way, that is called lambda. That is the wavelength. Velocity of light c, you are denoting it by c, are related by this equation, that is c is equal to nu into lambda. This formula you have to keep in mind. This is very common formula. C is equal to nu into lambda. Always keep in mind, C is equal to nu into lambda. Nu means frequency and lambda wavelength. The other commonly used quantity, especially in spectroscopy, is the wave number. One more term is there, wave number. This is also generally it is used in spectroscopy, and its unit is per meter, meter minus 1 per meter, that is called wave number. Wave, and you can tell it is defined as the, that you can this definition I am talking about for the wave number. It is defined as the number of wavelengths per unit length. Its units are reciprocal of wavelength unit, that is the meter minus 1. However, commonly used unit is per centimeter. Commonly we are using unit, that is the per centimeter, not SI unit. That I have discussed. Now some properties of electromagnetic wave. Now I want to just discuss some numericals, and then how to use formula. Only one formula I have told you, only one formula. Then that formula actually is used in solving many numericals, that is equal to C is equal to nu into lambda. Yes, only this formula you keep in mind. And velocity of light, that is 3 into 10 to the power 8 meter per second. Then many problems based on electromagnetic wave, you can solve it. Just I will try to convince you by giving some examples. Suppose I am just reading the question and then I will explain you. Just try to understand concept. After that, automatically you will solve. Then I told you, before solving the numericals, you have to remember velocity of light and this relation C is equal to nu into lambda. These two things you keep in mind, and frequency unit is S minus 1, that you are knowing, and lambda wavelength, that is in meter or per centimeter, sometimes nanometer. Then this you have to keep in mind, and also sometimes they will give that is in wavelength they will give in angstrom also, meaning 1 angstrom is equal to 10 to the power minus 8 meter, that you can convert into the centimeter also. Then that time it will come 10 to the power minus 10 centimeter. Then these things you keep in mind before solving the numericals. Then now I am giving the first example. This is a common example. The Vivid Bharatiya station of All India Radio, Delhi, broadcast on a frequency of 1.368 hertz, kilohertz means 10 to the power 3 hertz. And there, suppose it is broadcasting on 1368 kilohertz. Calculate the wavelength of the electromagnetic radiation emitted by transmitter. Which part of the electromagnetic spectrum does it belongs? Very simple question. Here they are asking question in that what is asking, calculate the wavelength you have to calculate. Then wavelength formula is already relation told you, C is equal to nu into lambda is wavelength. Then what will you that you can say wavelength? The wavelength is equal to lambda is equal to C upon nu. Then C value is you are well known, 3 into 10 to the power 8 meter per second, and nu value is given in question, that is a 1368 kilohertz it is given. Then very simple way, put the value in this formula, C divided by nu. Then C is equal to 3 into 10 to the power 8 meter per second divided by 1368 kilohertz. Kilohertz, just for the kilo you write 10 to the power 3, and for the hertz you write per second. Then you can see here, upside is meter per second, 3 into 10 to the power 8 meter per second velocity, and now down it became 1368 into 10 to the power 3 per second, and per second will cancelled out, then only meter will remain. Then after solving this, it will become 219.3 meter. Then radio wave, you should know, this comes under the radio wave. For radio wave, its wavelength is longest, highest you can tell. For radio wave, wavelength is highest, and for UV rays or cosmic rays which is found in the interior of sun, frequency is highest, frequency is highest, and for this frequency is least. For the radio wave, frequency is least, and frequency and wavelength both are inversely proportional. If frequency is more, it means wavelength is less. If you can say frequency is less, then wavelength will be highest. Then radio frequency has highest length, hence frequency highest length, then frequency will be very less. And frequency and energy both are directly proportional. More the frequency, more the energy. Don't forget. More the frequency, more the energy. Then cosmic rays, which is found inside the sun, its wavelength is highest, means highest energy. Radio wave, its frequency is least, then energy will be least. And always keep in mind, frequency and wavelength are inversely proportional. If frequency is highest, wavelength is least. If wavelength is least, frequency will be highest. Then here 219.3 meter comes. Then this is coming under the range of radio wave. Then this I have discussed about the, you can say, use of formula. Common formula, lambda is equal to C upon nu. Now another example I want to tell you, then again further it will be clear. Don't fear from the long question. Just try to understand what they are asking and use the formula. Then now question is like that: the wavelength range of the visible spectrum extends from violet, means 400 nanometer, to red. This is the range, 400 to 750 nanometer. It starts from the violet 400 and it goes up to the red 750 nm. This is the range, 400 to 750 nm. Very simple question is there. Express these wavelengths in frequency. Express these wavelengths in frequencies, hertz. See, very simple question. Express this wavelength. This is the wavelength 400 to 750. Express wavelength in frequency, hertz. 1 nanometer is equal to 10 to the power minus 9 meter. This also you keep in mind, this is common. 1 nm, nanometer, is equal to 10 to the power minus 9 meter. Then now again you have to use simple formula. Frequency is equal to C upon lambda. I told you C is equal to nu into lambda. That formula you are using here. Here frequency you want to calculate. Then frequency, that is a nu, is equal to C upon lambda. Then C value, you know, 3 into 10 to the power 8 meter per second. And lambda, because they have given minimum to maximum range 400 to 750. Then you calculate 2 times. First time for the 400 and second time for the 750. Then first you calculate for the 400. Then C upon lambda, then C is equal to 3 into 10 to the power 8 meter per second divided by 400 into 10 to the power minus 9 meter. That is the this they have given in nanometer. That's why nanometer is converted into the meter. How? Then 1 nanometer is equal to 10 to the power 9 meter. Then for 400 nanometer, just simply have to multiply. Then that value we are keeping here. Hence means C upon lambda is equal to 3 into 10 to the power 8 meter divided by 400 into 10 to the power minus 9 meter. Then meter will cancel. Then which unit will remain? Only per second will remain. Then after solving, result will come 7.50 into 10 to the power 14 per second. Per second is called hertz, Hz, capital H, small z, hertz. Then like that way, frequency of red light means 750 nanometer. For that also you should calculate frequency nu, same formula, nu is equal to C upon lambda. Then again put the value of C and put the value of lambda. Then 3 into 10 to the power minus 8 meter per second divided by 750 into 10 to the power minus 9 meter. This lambda nanometer 750 also converted into meter. Then it becomes 750 into 10 to the power minus 9 meter. Then now again meter will cancel, only per second will remain. Then after solving, result will come 4 into 10 to the power 14 hertz, that is the per second. Then like that way, now you have calculated frequency, and then what will be the range? That was in nanometer. Now it became you can say 4 into 10 to the power 14 to 7.5 into 10 to the power 14. This is the range you have converted. In the question it was in nanometer, 400 nanometer to 750. Now we converted into the, you can say, hertz. Then this is very simple numericals, and last one more numericals I will discuss. This is also very simple and easy. Question is like that: calculate wave number. Wave number they have given. Don't confuse. Wave number very easy. Then calculate the wave number, and second frequency you have to calculate of yellow radiation having wavelength 5800 angstrom. Question is very simple question. Wavelength they have given in angstrom, 5800 angstrom. Then now you have to calculate first wave number and second frequency. Then first you calculate the wave number. Then wave number, how will calculate? 1 upon a lambda, that is called wave number. 1 upon lambda. Then lambda, one more thing, wave number is represented just like a nu and bar. A small nu, just like a V you are writing, that is a V, and a small line upside, that is called wave number representation. Bar, what you are telling? Nu bar. Then wave number is 1 upon lambda. 1 upon lambda. Then first you have to calculate the lambda value. Then 1 upon lambda, that is the wave number. Then lambda, very easily, already wavelength is they have given. Then 1 upon lambda. The wavelength already given 5800 angstrom. Then lambda is equal to 5800 angstrom A. Angstrom means A, capital A, and one subscript 0 upside you have to write. Then lambda is equal to 5800 angstrom, that you convert into the centimeter. Then I told you 1 angstrom is equal to 10 to the power minus 8 centimeter. Or if you want to convert into meter, then 10 to the power minus 10 meter. 1 angstrom is equal to, and directly you can write 10 to the power minus 10 meter. Hence 5800 angstrom means 5800 into 10 to the power minus 10 meter. It is meter. If you want to convert into centimeter, divide by 100. Then obviously 20 will be less. Then it will become 10 to the power minus 8 centimeter. Anyhow, you have converted into the meter. 5800 into 10 to the power minus 10 meter. Then now this wave number is equal to 1 upon a lambda. Then 1 divided by this value. Then means 1 divided by 5800 into 10 to the power minus 10 meter. Then result will come 1.724 into 10 to the power 6 per meter. Or if you want to tell in centimeter, then 1.724 into 10 to the power 4, because meter you have converted into the centimeter. Then now it became 1.724 into 10 to the power 4 centimeter. Then very easy, you have converted the wave number, and now frequency very easily you can calculate. Frequency C upon lambda, put the value of C, 3 into 10 to the power minus 8 meter per second, divided by lambda. Lambda already you know 5800 into 10 to the power minus 10 meter. Then again meter will cancel, then only per centimeter will remain. Hence after solving, result will come 5.172 into 10 to the power 14 per second. Then like that way all numericals are very easy. All numericals based on my radiation, electromagnetic radiations are easy, only you have to understand the question. Okay, today I am stopping only here, and next class, next lecture again we will meet. Thank you.